I'm Mason, this is Cody. We have the Gaussian.
We chose the Gaussian integral because we just Googled cool calculus topics. We saw the Gaussian integral and went with it, and we had no idea what we were getting ourselves into.
So some topics that are involved with solving the Gaussian integral are multiple integration, partial derivatives, converting Cartesian to polar coordinates, matrices, and substitution.
So a little bit about Gauss. He was born on April 30th, 1777 in Brunswick, Germany, and he died on February 23rd in 1855. He was a German mathematician who contributed significantly to many fields including number theory, algebra, statistics, analysis, differential geometry, geodesy, geophysics, mechanics, electrostatics, astronomy, matrix theory, and optics. And a couple of those, like quadratic reciprocity, just solves any quadratic using arithmetic. And he helped develop the prime number theorem, which is the distribution of prime numbers among the integers. That's Gauss. And this is what we will be showing you how to solve. The Gaussian integral is the integration from negative infinity to infinity of e to the negative x squared, and it equals the square root of pi. So we're going to take in the Gaussian integral from negative infinity to infinity and set it equal to I. And then we're just going to use a dummy variable as x and y. So we're going to say that I equals the integration from negative infinity to infinity of e to the negative x squared, and it also equals the integration from negative infinity to infinity of e to the negative y squared. And that will get us I squared by multiplying both of them together. So then we have I and I to get our I squared. And then we can change it to a multiple integration problem. So it's the integration from negative infinity to infinity of e to the negative x squared plus y squared by distributing out the negative of dx. Then that integrated from negative infinity to infinity of dy. And then we're going to convert it to polar. So then we change our bounds, we get 0 to 2 pi of d theta. And then from 0 to infinity of r to the e to the negative r squared, since the x squared plus y squared is r squared according to polar laws. So then I squared equals 2 pi times integration of 0 to infinity of r times e to the negative r squared dr.
Now I know you may be wondering where this r came from. Well, let me tell you. It's called the Jacobian r, which is something that you need to multiply by when you're converting Cartesian to polar coordinates. And we dived in to figure out how in the world you find this, how they got the r. And it's a matrix of these four partial derivatives. dx dr, dx d theta, dy dr, and dy d theta. Now you might be wondering, how do you get partial derivatives? Well, we said x equal to r cosine theta, y equal to r sine theta. When you take a derivative, a partial derivative, you take it with respect to one of the variables here, because we have two variables in each. So dx dr is we're going to take the derivative of x in respect to r, meaning anything using the other variable acts as a constant. So
The derivative of the r is
basically,
1.
yeah, and so cosine theta, so it's basically as if it's 3r. Pretend that you get 3. Cosine theta becomes a constant, and so it's just left with cosine theta. Same way, the other way, the r acts as if it's just another number, and we get r sine theta for dx d theta. Same concept over here for the y. So now take all those four partial derivatives and put them into this matrices. Now, if you remember how to solve matrices, it's this. These two minus these two. So we take this, we get r cosine theta times cosine theta minus a negative r sine theta times sine theta, which equals r cosine squared theta plus r sine theta squared theta. Factor out the r, and we get cosine squared plus sine theta squared theta is 1, so we got r. Well, yeah.
That took us like 3 hours to figure it out.
Okay, so now we're back to our original.
Back to our original integral I squared equals 2 pi times integration from 0 to the infinity of r e to the negative r squared dr. So now we're going to use substitution to solve. So we're going to set u equal to r squared. So du dr equals 2r. Then du will be 2r dr. And dr will equal du over 2r. So we'll plug that in for our I squared. So we plugged in our dr over here, and the 2r, the r will cancel with this r, and the 2 will cancel with this 2, and then we'll add e to the negative u, and it'll leave us with I squared equals pi times the integral of 0 to infinity of e to the negative u du. Which now we'll start solving, and we'll have I squared equals pi times negative infinity, or negative e to the negative u from infinity to 0, or from 0 to infinity. So we're going to plug in infinity here and subtract it from e to the 0, and that'll give us pi times 1. And so I squared equals pi, and I equals the square root of pi. Yeah,
That's what the graph looks like. So now we get into the Gaussian function, which is where this applies to statistics. Just basically a little bit of a variant from the original e to the negative x squared, using mu and sigma for the mean and standard deviation and variance. So what we did is we took the mean, mu, and variance sigma squared gives probability that a random continuous variable lies between a certain interval, which is what you're integrating from. So we just took, with mean 0 and variance 0.5, we took what's the probability that a point lies between 0 and 0.5 on this graph, and it equals 26, around 26%.
and then this is just a graph of that previous problem that Mason just went through, and this is our standard deviation. Our variance is what the standard deviation is squared. So a law of a normally distributed probability function is that 68.2% of the data is distributed within one standard deviation, negative and positive, and then 13.6 for another standard deviation, and so forth. And then after 3 standard deviations, you typically have almost all the data. It's like 99.8 for each.
So basically Gauss's function is what helped us to see this.
Okay, so Mr. Kruger has 184 students in his calculus 2 class. The scores on his impossibly hard final are normally distributed with a mean of 72.3 and a standard deviation of 8.9. How many students in the class can be expected to score between 82 and 90? Express the answer to the nearest student. So we're going to use our function, and we're going to have mu of 72.3, which is our mean, and variance of 8.9, which is given to us. So we're going to plug in all those, our mu and our variance into this equation, and have f of x equals 1 over 8.9 times the square root of 2 times square root of 2 pi times e to the negative x minus 72.3 squared divided by 2 times 8.9 squared. And then we're gonna integrate from 82 to 90, since that's the range that we're trying to find, the percent of students. And then we're gonna integrate f of x and get 11.45%. And you take 184 students times the 11.45%, and you get roughly 21 students are going to be within that interval of how they scored on the test.
Calculus student sanity is normally distributed with a mean of 500 days, and the standard deviation is 61 days. The nearest percent, what percent of students retain their sanity for longer than 561 days? So we have our mean of 500, our variance of our standard deviation of 61. Plug it into that same equation. Integrate from 0 to 561. It's 84.3. We take 100. Because it's asking what percent is more than 561. 1 minus 0.8413 is 15.87, or 0.1587, so we have 16% of students retain their sanity.
This is how humanity Gauss felt when he figured out all these problems.
Yep.
Wow.